Okay, moving on. By the time you've looked at number 14, if you've been doing the questions in order, you've probably seen a lot of these fencing type problems. This one's using tape, but it's the same general principle. So hopefully this one's not too bad once you've done a few. So police officer investigating a crime wants to seal the area around the crime scene with 300 meters of yellow tape, and it's going to be a rectangular area that he's going to enclose. So if you again picture a little crime scene here, maybe there's a dead guy right here. Okay, and he wants to enclose an area that's 300 meters around it with tape. Okay, we don't know the dimensions, so we're just going to call them L and W and define our variables that way. Okay, so there's my defined variables. L and W will be the length and width of the crime scene in meters. So we're looking to do work with the maximum area, so we need to try and write out our area equation, which is simply going to be area is going to be length times width. Okay, and we want to try to maximize that, so we need to find the optimal value to find the maximum area, the axis symmetry to find the dimensions, so we need to create an equation. And just like with all the other fencing problems we've seen, we've got too many variables over here, independent ones anyways, both length and width. So let's use the fact that we know that there's 300 meters of tape, and know that 300 meters is going to be equal to 2L plus 2W. Okay, because we have two lengths to make up this rectangle and two widths to make up this rectangle. So 2L plus 2W equals 300. So let's isolate for a variable. It doesn't matter which variable I isolate for, so let's just isolate for L. Okay, so I'm going to subtract 2W from both sides of the equation. So I'm going to get 300 minus 2W is going to be equal to 2L. Okay, and all that's left here is divide everything by 2 to get L by itself. Okay, so we get 150. 2W over 2 is just W, so 150 minus W is equal to L. Okay, so with that done, I can now substitute that into my original area equation. So area is going to be equal to, instead of L, it's going to be 150 minus W. And I have another W there. Okay, so now I have an equation in factored form. So what does factored form give me? Remember, I can use that to get my zeros. So my zeros are relatively quickly from here, I can see them. It's going to be at W equals 150 for that first factor. Okay, and at W equals 0 for the other factor. So my axis symmetry, which is going to be the width that gives me the maximum area, is going to be halfway between 0 and 150. So it's going to be W equals 150 plus 0, all divided by 2, which gives me 75. Okay, so width of 75 meters will give me the maximum area. I can find the length by substituting back into this other equation I create over here. So L is going to be equal to 150 minus 75, which is of course going to be, again, 75. Which is telling us that it's going to be a square to maximize the area. So width of 75, length of 75 will give me the maximum area. How do I find that, what that maximum area is going to be? Well, I can just use the original equation. So A is going to be equal to length times width, or I can use the one that just has width in it. I'll use that one. So I have 150 minus W times W, putting in my W equals 75 for my axis symmetry. I wind up with 75 times 75, which gives me an area of 5,625 square meters. Okay, so like all the other fencing problems, we need to create a second equation to eliminate a variable, and then work with our axis symmetry to then get our optimal value. Okay, let's take a look at another one. So the sum of the squares of 3 consecutive integers is going to be 2,189. Find the integers. Okay, so again, let's just start with the sum of the squares here. So you know that means we're going to be adding each of those numbers squared. We need to find variables for all of these values. So what I'm going to start with is I'm going to just let A be one of the consecutive integers. Okay, so I'm going to let a represent the first integer. What does that now? You got to think what it means if the numbers are consecutive. Well, it means that the first one's 5, the next one's 6, and the one after that is 7. So it's going to be the second number is going to be the previous number with 1 added to it, and the third number is going to be the first number with 2 added to it. So if we're going to let a represent the first integer, what we can then do, just to make things a little bit simpler, is let a plus 1 and a plus 2 be the next two integers. Okay, so we don't need to have 3 different variables necessarily for these 3 integers because they're all consecutive. So whatever the first one is, the second one's going to be 1 larger than, the third one's going to be 2 larger than the original one. So we know the sum of these squares is going to be 2,189. So what that means, we're going to have the first number squared plus the second number, which is a plus 1, all squared, plus the third number, which is a plus 2, all squared. And we know that the sum of those squares is going to be equal to 2,189. We want to find the integers that make this work. Okay, so again, with a situation like this, you're not seeing max or min. You know you have nothing to do with the vertex here. This is a solving type problem. So in order to solve an equation, we should get everything expanded out so it's equal to standard form, and then we can solve it from there. So so remember, everything here needs to be expanded out with an array. So a squared is just a squared. Okay. But a plus 1 squared, do not write as just being a squared plus 1. It does not work that way. We've seen that tons of times by now. You have to expand out a plus 1 all squared using an array. I'm going to let you do that on your own, but you should get a squared plus 2a plus 1 from a plus 1 all squared. Okay, similarly for a plus 2 all squared, you should wind up with a squared plus 4a plus 4. Okay, now that's going to be equal to 2,189. Okay, once you have this part done, again, I'm going to leave this algebra to you to get from a plus 1 squared to this and a plus 2 squared to this. We need to collect all of our like terms. So I have 1, 2, 3a squareds. I have 2a and 4a, which gives me 6a. And I have 1 plus 4, which gives me 5. So 3a squared plus 6a plus 5 is going to be 2,189. Okay, and I cannot solve this quadratic equation unless it's all equal to 0, so I'm going to subtract 2,189 from both sides of the equation to get negative 2,184. So I have 3a squared plus 6a minus 2,184 equals 0. Okay, so once I have my equation in standard form and equal to 0, I can either do factoring or using quadratic formula. So I'll do a quick check to see if it factors. I'll check my discriminant. So my discriminant is going to be equal to b squared minus 4ac, so it's going to be 6 squared minus 4 times 3 times negative 2,184. Okay, which when I work out is going to give me 26,244. And when I check that on my calculator, I'll see that it is a perfect square, so it is factorable. Okay, so I'm going to try and factor it. Again, if you find quadratic formula faster in this situation, especially with the larger numbers that are involved, feel free to use that. But again, I'm going to factor it because I think it's good practice, but we should wind up with the same answers in the end. So to factor this, I'm going to look for a GCF here, and I'm going to see if 3 goes into everything, and it turns out it does. So I'm going to factor out the 3. That's going to give me a squared plus 2a minus 728. Okay, so to factor this, even with the ugly numbers, it's still going to wind up being a simple trinomial. So I need two numbers that multiply to negative 728, but add to 2. Okay, so I'm going to do a little bit of trial and error here, try and work out those two numbers. Okay, it turns out those two numbers are going to be 28 and negative 26. So that gives me 28a, negative 26a. So I get a minus 26 and a plus 28. Okay, and again, if you use quadratic formula, you should get the exact same answers in the end, but it might take you a little bit longer or a little bit shorter, depends how fast you are with factoring. Okay, so from here I get two possible answers. So from this first factor I get a being equal to negative 28. Okay, and from this one I get a is equal to 26. So remember what I've solved for here. What I've now solved for is the first integer in each case. That's what a was. So the other integers are going to be those two numbers plus 1 and those two numbers plus 2. So that means using the a being negative 28, and again, there's nothing wrong with having a negative integer. It's a possible answer. It's not a length, so it's perfectly admissible. So it means my answers here are going to be negative 28. Then the next two numbers are going to be negative 27 and then negative 26. That's one possible answer. And then from here, I'm going to wind up with the numbers being 26. Adding 1 gives me 27, and adding another one gives me 28. So I have two possible sets of answers, and each of them are going to be three consecutive integers starting with my values of a. So the answers can be 26, 27, 28, or negative 26, negative 27, and negative 28.